All right, so this one video is going to be all about temperatures. Well, we've talked about how the atmosphere gets energy from the sun, and energy can be related to heat. You think about it, molecules all move. So molecules move more the faster they move, the higher the temperature. The less they move, the colder the temperature. So in the atmosphere, when you get molecules moving a lot, interestingly, the atmosphere is non-compress is compressible. So what the heck does that mean? That means that we can take a volume of air, and if I heat that volume of air, it's going to expand and take up more space. If you heated the same thing of water, it wouldn't move much. It wouldn't change area. But if you do air, air expands, so these molecules are pushing each other apart. So the hotter the air is, the less molecules are in one given space. Has a dramatic impact on the weather. So why did this happen here? As far as this is Mansfield, Ohio, and I just do it. There are a couple, it's a meteogram. A meteogram has several things plotted on it. Temperatures, time is always on the bottom. So with the time here, this is 3 days. We have a dew point. With that, we have a relative humidity. And finally, the blue is temperature. So we started out with temperature at 73 degrees. Right here, you can really see the dew point came up significantly. Temperature dropped. Relative humidity went up. I'm betting it's rainy in this time frame here. And then right here, temperature, dew point really starts to go down. So while the temperature held in the 70s, the dew point went down significantly, much drier, and this is in the daytime. So probably a cold front went through here, and you can see the temperature is down. And temperature really cooled off then at night. So why did it cool off at night? Not any energy. Warms back up during the day, cools back off at night, comes back up again. Much cooler than at my house, this temperature's readings are. My house has been in the 80s and 90s a lot of the same time period here. So all of this is causing a difference in temperature across an area. If I was to look, for example, at today's temperatures, a lot of them are in the 70s across Ohio right now, maybe low 80s. A lot of northwest winds coming off the Great Lakes up in here and stuff. Notice the air temperature over the lake, 62 degrees over the Great Lakes, even though the air temperatures around it are in the mid 70s. So another question, why are the lakes cooler than the air around them? So I'm going to talk about some of that. Let's learn what causes temperatures to change. So with this, we'll start this slideshow and we'll talk about heat, temperature, and atmospheric circulation. So what are the causes and consequences of heat transfer? Heat is not temperature. Heat is energy in motion, we'll say. One of the hottest areas in the world is Death Valley. I don't know if you've ever driven across parts of California that are near Death Valley. We went to Bakersfield a couple times and we drove across kind of the edge of Death Valley. Temperatures were in the hundreds and it was very, very just dry looking, not much around. And that's what Death Valley is actually also below sea level. So all of that dryness, intense sunshine, below sea level contributes to very, very record high temperatures. Matter of fact, in 1996, 40 days in a row, the temperature was above 120 degrees. So here's a little bit about the topography and all. Interestingly, average high temperatures and low temperatures, they can get pretty cool at night, sometimes into the 30s. And yet the average highs can be in the hundreds, well up in the hundreds. So very extremes in the temperature here. In other words, you could be burning up during the daytime and be at night, you could be almost too cold. So temperature. If you looked at a molecule, most of us can't look at an individual molecule. Uh, there's a kinetic energy with that molecule. Basically, the electrons and all are moving. The faster they move, the more kinetic energy that molecule has, the higher the temperature is. The slower they move, the less kinetic energy that molecule has, the cooler the temperature. That is everything related to temperature. So if I tell you the temperature outside is 110 degrees, those molecules are moving pretty quickly. If I told you it's minus 20 degrees, molecules have slowed down. So that is what temperature is. So how do we change this temperature? Heat is just energy in transfer. In other words, if the temperature dropping, heat is being sent away from that object. If the temperature is rising, heat is coming to that object. Energy is being transferred. So we need to understand these processes, how energy moves in the atmosphere. There's a scale called the Kelvin temperature scale. The Kelvin scale is if you were freezing something 273.15 degrees Celsius is and Kelvin is the freezing point of water. Absolute zero of Kelvin means that molecules are not moving at all. We can't have anything below that because molecules can't reverse energy or not, if they're moving at all, there's energy there. So that is the absolute minimum of Kelvin temperatures. Another interesting thing with temperatures is we talk about the heat transfer. Well, there's something called a calorie, and it's not the same as food calories. It takes the amount of heat, energy coming in to raise 1 gram of water 1 degree Celsius. Now, if we relate that to something that meteorologists use, which is a joule, 1 calorie equals 4.1868 joules. British thermal units is another measure. It's English units. 1 pound of water, 1 degree Fahrenheit would be 1 BTU. These are different ways of measuring heat transfer. You look at a thermometer, you can see how heat temp changes because you can see how the thermometer sees the temperature changing. We measure to about a half a degree Fahrenheit. Most National Weather Service thermometers do. So technically, if it's 97 degrees, the temperature could be anywhere from 96.6 to 97.5. Somewhere in that range the temperature is. We also have another thing called temperature gradient. Gradient is change in temperature over distance. So we'll say, since I'm teaching this course for Mount Vernon, we'll say you're in Mount Vernon. Temperature in Mount Vernon today is 95 degrees. You're driving to Columbus, Ohio, which is not that far, I know, because I've driven it. And the temperature there is 65 degrees. So somewhere between Mount Vernon and Columbus, Ohio, there's over a 30-degree temperature change. That is the gradient of temperature. The stronger that gradient is, the faster temperature can change, either up or down, depending on which way it's moving. And according to the second law of thermodynamics, heat always flows in response to that temperature gradient. And it always goes towards the lower temperature to eliminate the gradient. So the more energy, which is the hotter the air is, always flows towards the colder. So that is a key fact in anything with weather, working with weather. We got to understand that heat is always going to try to eliminate the temperature gradient, and it's always going to go from the hotter to the lower. The atmosphere hates temperature gradients, to be honest. It would like everything to be uniform. Can't do it because of the way energy rises in the earth, but it's always working to do that. And how does it transfer the energy? Well, we talked about radiation, yes, on the other video. Conduction is another one, convection is one, and latent heat. So, radiation is just energy passing through space. Microwaves take energy that they produce and pass it through air into the object, heating the object and making it nice for dinner. We know the sun translates it. Conduction. If you put your hand down on a hot object, you're burning your hand, you're getting it off of there quick. That is conduction. So the molecules, the heat that's there in the warm surface transfers to your hand. Cool, trying to heat your hand up. That's conduction. Same thing happens in the atmosphere. If you have a very hot ground, conduction is trying to warm the air, especially in the lowest part near the ground. Some things can definitely move heat better than others. There are different metals that transfer heat very well, and water is not one of them. The liquid that does not transfer. Dry sand does not transfer, and air is a very poor conductor of heat, one of the most. There's also, because air is a fluid, convection occurs. Convection is where you warm the bottom of the air. It starts to rise up, cools, then goes back down. If you ever look at bubbles that you can see in your pan when you're boiling water, that's convection. Water is a fluid, air is a fluid. And if we combine convection and conduction, we get what we call sensible heating. So if we took out any moisture, don't worry about it. Sensible heating is always going to just be convection and conduction. However, sensible heating does occur. Latent heating, does occur because there's moisture everywhere in the air. And what that means is, and interestingly, water is the only element in the air that changes state in our normal temperature ranges. So, as an element of water goes from vapor to a solid, it loses energy. In other words, a solid doesn't need as much energy to stay solid as water vapor does to be a gas. So as it goes down that range, if it goes from a gas to a liquid to a solid, it is losing energy. Energy is going from that out into the atmosphere. The opposite way, if it goes from a solid to a liquid to a gas, more energy is being absorbed. So the atmosphere is actually giving energy to that liquid or that water and eventually turns it into a vapor. That changes the temperature in the atmosphere because there's latent heat, energy transfer that goes on from the atmosphere to the water. Water has an extremely high specific heat. In other words, it takes a lot of energy to make the water warm, even 1 degree. With that in mind, you think about the oceans. So there's a very resistance to oceans changing temperature fast. If you're out off the Atlantic coast sometimes in the summertime, you'll find temperatures running in the 70s, maybe mid 70s with the temperature in the water. It took a lot of energy to raise that water to that temperature. And also, in the wintertime, will take a lot of energy from the water for it to lower back down into the 40s and 50s. So anywhere you live along a coastline or along a water body, there's going to be a moderation of temperature. And you can see it here in a maritime climate, such as San Francisco. Not a lot of temperature change from the summer to the winter. However, St. Louis, continental climate in the middle of the country, has no ocean around it. Pretty significantly change in temperature between the seasons. So, the Earth's surface absorbs solar radiation, and then it's re-emitted back into the atmosphere as infrared. And that infrared radiation is then sent out into space. Earth's surface undergoes net radiational cooling. So I want to talk a little bit more about transfer of heat here due to radiation. There are all kinds of things impacting radiation here. We have solar radiation coming in. Some of it's absorbed by the atmosphere, some of it's scattered back from clouds, some of it's reflected off the earth. Some gases store it, like it says, and some of it's absorbed in the surface. Then we have infrared radiation, long wave, outgoing. And what happens? We have, greenhouse gases grab some. But something does go all the way through. Latent heat flux sends this atmosphere out. So it's a very complex system on how the atmosphere heats and cools itself with time. Here you can see heat transfer being conduction and convection. And you get these big clouds, cumulus clouds up sometimes. They're great transfers of energy from the surface of the earth well up into the atmosphere. Why is that? Well, they start out as convection and sensible heating, conduction, heating the lower level of the air, beginning to rise. As it rises, the air is cooling. As it cools, water vapor condenses. When water vapor condenses, it releases heat. We've gained some more heat. So as we go up, we're gaining heat from the conduction, convection, and latent heating. All of that heating is getting pushed up in the atmosphere in these cumulus clouds. And here you can see the Bowen ratio, which is really a ratio of sensible heating to latent heating. The more latent heating, more moisture available, the slower the atmosphere temperature is going to change. More sensible heating, the drier the air is, the more the atmosphere is going to warm. One of the things meteorologists actually look at is what kind of weather, precipitation, has occurred in the last week or the last several weeks. If there's been a lot of rain, we know warm temperatures are not going to warm as much during the day because some of that energy coming from the sun is going to go into evaporation. However, if it's very, very dry, like happens in deserts, we know that a lot more energy is going to come in, hit the earth, and raise temperature more. So it actually impacts how we forecast temperature. Here we can see the poleward transport of solar radiation, and we want to do that because the poles would really, really, really be cold. They're not as cold as they would be because we have air masses that exchange heat, storm systems, and even the ocean transfers heat from the equator up to the poles. Air masses are just large volumes of air. They can cover several thousand square miles, and they form over land or water that's generally uniform. So the temperature is typically very close to the same. The relative humidity is very close to the same over that whole air mass. And these air masses travel around the world. Some places around the U.S. that form air masses are over Canada, the desert southwest, maybe the tropics down off the east coast of the United States. So why is there weather then with all of this? I've just talked about all this temperature transfers and all, because the winds, convection, transfer of heating, all of that causes storms, causes clouds, causes change in temperature, all of which we would consider changes in the weather. So here's the local radiation that arrives in different spots. For example, here in Brazil, not much change throughout the year. Kansas City, less in the winter, more in the summer. And we get way up in Canada, not a whole lot in the winter, significantly more in the summer. And you can, with that local radiation budget, that is what drives these changes in temperature. Even during a day, interestingly, our high temperatures almost always occur in the mid to late afternoon. If it's a typical bright, sunny, not much wind day. Why is that? Well, during the day, there's a lot of infrared a lot of ultraviolet sun radiation coming in. So it exceeds the infrared radiation leaving the Earth, even though temperature is rising. And as long as there's more radiation coming from the sun than there is infrared radiation leaving, the temperature of the air is going to keep warming. The maximum infrared radiation is around noon, but it keeps warming the rest of the afternoon until we reach the point where they're equal. Once they equal them, and the infrared radiation now is going to become more than the sun's radiation coming in, temperatures are going to begin to drop. And they'll particularly drop maybe a little bit faster early on, just because the temperature is warmer of the air. Warmer air, more infrared radiation. We learned that last time. So that'll move it, make it cool quicker at the beginning of the night and then slow down later in the night. Things like bare soil can absorb more energy. Snow, on the other hand, has a really high albedo. There's not a lot of sun's energy that makes it to the Earth's surface and warms it if we have a lot of snow. Air mass advection, so cold air advection can definitely bring in much colder air. Warm air advection brings in warmer air. We think of this when cold fronts pass. This is the air masses coming in the wintertime. Last winter, you had some significantly cold air masses that would move through, change the temperature significantly. That's cold advection. And there are things like urban heat islands as well. In the middle of cities, can be significantly warmer than other areas. So really covered a lot of information here. Let me know if you have any questions on all of this.